All right. Yeah. So this problem, we need to solve a technical problem that the location of the initial value is not right. So we want to make it right. Right? Yeah. So we need to do some work, some transform, special transform. So now I want to explain the special transform. Yeah. So the shift operation, let's review slightly. Yeah. I'm afraid some students may not be familiar with that. Actually, it's very simple. Yeah. Suppose we have a function, f function. Suppose this is the graph of the, yeah, let me use the, sine cosine shape. Yeah, because we have peak thing, right? We have peak thing. Yeah. Yeah. This is f of x. Yeah. All right. Now, let's look at the graph of a function f plus 1. Yeah. Or f minus 1. Yeah. Plus minus. Yeah. So we'll see. Let's look at the f minus 1. Okay? Yeah, it's better. I draw the graph. I really use the sign. Yes. Because sign has a special property. At a 0 point, the function value is 0. Okay? Yeah. So that's give us some reference, good reference point. All right. Now, I want to ask you how to draw a graph that is f of x minus 1. Okay? Now, you use that reference point. Okay? So when x equals 1, f of 0, right? Yeah. So you look at the x equals 1. That's the new reference point. When x equals 1, that's here. That's here. 1. Then it is a, starting 0 point. So, yeah. Let me use the, use this way. All right? Yeah. So you can see it's a shift operation. The graph of the curve is shifted 1 unit to the right. Okay? Minus, that means the shift direction is you move it to the right. Plus, you should shift to the left. Right? Yeah, so plus, minus, shift to the right, to the left. All right? So based on this understanding, now let us do some shift operation. Yeah, so now we can define a new function, using the appropriate shift operation. Yeah. All right. Oh, sorry. Yeah. This remote control, I should put it in this laptop. Then, yeah. So I can make it work. Yeah. All right. Now define y tilde function closely related to y, but with some appropriate shift operation. This time, plus pi over 4. Why plus pi over 4? You can see when t equals 0, so here, the reason we use that is y tilde 0 equals y pi over 4, right? That's the, original initial value. The first original initial value. But from the form, you see it's a y tilde at 0. 0, that's the special point we want to have in our derivative formula. Okay? Yeah? So you can see we get around, this technical problem. All right, then let's plug in. Let's apply ODE on this y tilde function. Yeah. All right. Yeah. So here you can see, if we calculate the derivative of y tilde prime, very easy. Yeah. pretty straightforward. Double prime, also pretty easy, straightforward. Yeah. Chain rule, right? We use chain rule. So this is a composite, simple composite function. The chain rule, yeah, but chain rule, very simple. Yeah. All right. Then the initial values, y tilde of 0, some value, y tilde prime of 0, some value. Yeah, known value, right? Yeah. Now we are ready to convert the original equation to the new y tilde version equation. Yeah. Tilde version, this is original equation, right? Yeah. But to do the conversion, we replace this t by that shift version. Yeah, because we want to do some shift operation. So we replace t by t tilde plus pi over 2. It's some variable substitution, which introduced that tilde variable. But tilde variable, we know it's a dummy variable, right? Yeah, just a variable. Yeah. But to see the structure change, so we intentionally, we bring a new variable, t tilde. Yeah. So t equals t tilde plus pi over 2. Yeah. So then we just, plug in, replace in the original equation, so we get this newer version, right? Yeah. This newer version, you can see we set up special structure. Yeah. So that's the structure we want to put there. Yeah. With this structure, can we convert it to the tilde version, right? Yes, sorry. This is the tilde version and y version, right? Yeah. So from this equation, we can go to the ODE of that tilde y version. Yeah. So, because by definition, by what we did before, so we have this y tilde double prime plus y tilde equals 2t tilde plus pi over 2, right? Yeah. So here the variable becomes t tilde, but that variable, tilde or not, it's not important, right? Yeah. So if we change back to t, that's okay, right? Because that's just a variable, right? T tilde or t, it's not important. Yeah. Yeah. All right. Then we need to apply Laplace transform. Yeah, because this time the initial condition is good. Yeah. Now we can apply. So we need to use the basic formula. One is here, another one constant. Yeah, because this 2 pi over 2 times constant, right? So we need a Laplace transform of one constant. Yeah. Then we apply it to both sides. Left-hand side is this the double prime Laplace transform? Yeah, Laplace double pi over s, right? Yeah. Oh, sorry, the 3 terms. The first 3, that's the double prime Laplace transform. Yeah, first 3. Yeah. Then, yeah, that one. Yeah. All right. After that, we need to solve this algebraic equation after simplification. Yeah. Yeah. Left-hand side, right-hand side. Yeah. Then y, capital Y prime, tilde. So we get this long expression. Yeah. So next, we need to do the inverse Laplace transform to find the solution. Yeah. So next slide. Yeah. Let's do the inverse Laplace transform. Yeah. Y tilde. All right. Inverse by the linear radial principle. Yeah. There are 4 terms. Linear radial principle. So we can apply the inverse Laplace transform one by one on 4 terms separately. Yeah. The first one, constant out, Second one, constant out. Third one, constant out. The last one, also constant out. Okay? Yeah. There. Next, we need to find appropriate formulas. All right. Yeah. Appropriate formula. Let's write down sine, cosine. Yeah. First. Yeah. All right. Look at the last one, inverse Laplace. Can we get the inverse Laplace transform from this one? Omega equals 1. Yeah. So the last term, we have it. All right. Then, the second to last, also omega equal to 1. Yeah. So this inverse Laplace transform, we have it quickly. Yeah. Then, we only need to work on the first two, inverse Laplace transform. All right. Let's work on this first. When we look at the structure, I hope you can see the structure here. 1 over s, s times another s function. Yeah, that's a division, right? 1 over s, division by fs. Division, then we have a formula. Look at this formula. Okay. Division by s, right? 1 over s times a capital F function, then inverse Laplace transform equals the integral of that little f function. That's the key formula we need to use here. Okay? Yeah. So here, capital S f function, capital F of s here equals 1 over s squared plus 1, right? So that is the sine. That is the sine. Omega equals 1. Okay, omega equals 1. That means little f of t equals sine of t. Yeah. So we have the little f. So we do the integral with that little f. All right. Yeah. So here you can see the inverse Laplace transform by this integral formula. Yeah. We just do the integral on sine of t. Yeah. And it is this. Yeah. Yeah, because here y tilde, so we still use the little t tilde. Okay? Yeah. Corresponding to y tilde. Yeah. That. All right. The last term, the first one. How to do the first one? How to do the first one? Yeah. First one. Okay. First one, you have two ways to do it. Two ways to do it. One way is this function multiply 1 over s. That function, we just multiply another 1 over s. Then we can apply this formula again, but this new capital F is this function. New capital F is that function. Yeah? So we do the integral. That's the first method. So here, let's do the first method. So inverse, yeah. So then we take the integral on that new little f s function. So this is the new little s function. Yeah. All right. After that, so we get this integral. That's the first method. Yeah. Yeah. The second method, yeah. Let me complete this whole solution. Then I talk about that second method. So let's keep going. Yeah. So we find inverse Laplace transform for all four terms. So we combine all four terms. So we get a little y tilde represented with variable little t tilde. But we need to go back to t, right? Yeah. Because after we do the shift, we need to go back to, inverse that shift, right? Inverse that shift. So after we shift to the right, plus pi over 4. So shift to the left. So we should shift back to original location. Yeah. So let's shift back. Yeah. So we simplify it. Yeah. Simplify. So t is that. Yeah. T is that T tilde is T minus pi over 4, right? Yeah. So then we go back to the T. Yeah. Replace T tilde by T minus pi over 4. Yeah. That's the final solution. Yeah. So it is, so when you do things like this, you need to be very careful. Yeah. Each step, yeah. So you do the calculation carefully. Yeah. Right. Yeah. Yeah. But the idea, yeah, how to fix that wrong initial condition. The initial condition not quite right. Yeah. So you do some appropriate shift operation to make it right. Yeah. Then inverse, yeah, because that shift operation is a transform. Okay. After the transform, at the end, you need to apply its inverse transform to bring it back. Okay. Yeah. All right. Then I talk about there is another way to calculate this inverse Laplace transform. So the second way is, think about, if I give you this question directly, I throw out, yeah. So I do not give you other things. I ask you to calculate this inverse Laplace transform directly. So then there is an easier method you can use. So you need to decompose this fraction. Yeah. So here I try to let you practice. Yeah. Here, if I write it this way, s squared times s squared plus 1. We need to decompose this fraction. Yeah. You know partial fraction, but here it is so simple. We don't need a partial fraction, the standard method. Yeah. So we can use some shortcut, use our observation, so we can decompose it quickly. Can you see 1 over s squared minus 1 over s squared plus 1? Common denominator, then numerator, s squared plus 1 minus s squared. S squared cancel out. So numerator 1 over s squared times parenthesis s squared plus 1. Yeah. So I like you to use your observation. After you practice, you get experience. You can do this kind of decomposition quickly. Yeah. Then you can solve problems faster. Yeah. All right. So with this structure decomposition, if we want to calculate then, by the linearity principle, 1 over s squared first, minus linearity principle, the second, 1 over s squared plus 1. Right? Yeah. 1 over s squared, is it that t? Right? Yeah. Is it that t? Yeah. So here, inverse 1 over s squared, is it that t? Yeah, tilde, yeah. Here I talk about the general. Yeah, if you go to the, solution, then tilde. All right, yeah. But if I just throw this question to you directly. Okay, all right. So you just use t. You do not need to use tilde. All right, because here I want to remind you the Laplace transform of t to the m equals n factorial over s to the, let me erase this, s to the n plus 1. Okay, here n equals 1, yeah, because 1 over s squared. Yeah, so we have that. All right, then the second one sine, right? Sine this omega, right? Sine. So this one we can write t. Oh, now you want to get back to, yeah, right. Yeah, if we get back to this question, we use tilde minus sine t tilde. See? The same as the one here. Okay? Yeah. Good. Yeah. Here, just give you some, more examples. So let you practice a little more on Laplace transform. Yeah. So for module 2, I just do this much Laplace transform. Okay. Yeah. So we do the, basic properties. So then, the one shift formula, right? First the shift formula. We have the second shift formula. Yeah. But we have derivative integral. We have, those formulas. Yeah. That's the, we can do a lot of things. Yeah. So then the remaining Laplace transform I leave to module 3. Yeah. So after I complete the part E, so we complete module 2. Next, we need to move to module 3. Yeah. So next week, we need to move to module 3. Yeah. And because you will submit homework assignment 1 quickly, yeah, so by Friday, so it will be submitted. Then I need to make your second assignment covering questions on module 2. Module 2. So two assignments before the midterm. Yeah, because the midterm will be in mid-March, right? Yeah, approximately mid, yeah, something. Yeah, so I will double check.
Spring break is the 9th through the 16th.
Yeah. So probably I need to move after spring break. Yeah. Let me see. If it's a spring break, then in order to give you plenty of preparation time, I like to move after spring break. Yeah, because after you practice, after you submit second assignment, I need to do the grading and give you back and give you a review. So before midterm, I need to give you, complete review, explain all the solutions, yeah, including quiz questions. Oh, you need to do a new quiz. Yeah, so this week, yeah, let me assign you second quiz first. Yeah, to check your understanding on basic concepts. Yeah. After that, then I assign a new homework assignment 2. Yeah. So the weekend, I do not assign homework assignment 2. Okay, I assign quiz number 2. Yeah. So next week, about mid next week, I assign homework assignment 2. Yeah. So then, before spring break, you need to submit. Yeah. So after spring break, so then you need to do the midterm. Yeah. Something like that. Yeah. All right. Yeah. So we come. This is last example in part C. Yeah, part C. Yeah. All right. But before I move to, sorry, I spent too much time. Yeah. Before I move to the next topic in part D, yeah. So there is one question to think about. So here, because we do shift, you can see y initial value, y prime initial value given at the same location, right? Yeah. So another possibility is, although it's rare, okay, because in the real world application problem, usually the initial condition given at the same point. Yeah, most of the time. But here I like you to think about technical problem. In case, let me give you just a simple version. The first initial condition given at 0, the second initial condition given at 1, how about that? Yeah, because this shift operation won't work, right? Yeah, because if you take care of 0, you cannot cover 1. If you take care of 1, you cannot handle that 0 point, So there must be some, technical difficulty here. Yeah. So here I do not know how to do it myself. I just raise the question. Okay. Yeah. So raise the question. Yeah. So later, when we do review, probably I can talk about that. Okay, when I do review for the midterm, then if I have time, yeah, I can talk about this question, because I need to find a solution first. Yeah, I need to find how to solve this problem first. Yeah, so then I can explain to you. Yeah. All right. Now I want to switch to part D. Yeah, so this is part C. I hope my recording is fine. At the break time, I will check my video if the video is normal or not. All right. Yeah. So part D. Yeah. Last topic of. Yeah. So I hope I can use about 15 minutes to complete the last topic of part D. Yeah. Yeah. Because we did the previous one, we completed. Yeah. That's the older one. Yeah. Now this one, D.5. Yeah. Modeling of forced oscillations, resonance. Yeah. So that resonance problem. So actually the resonance problem today we will, yeah. Part D we cannot see that. Yeah. So yeah. So let me. So we only need to solve one example. Yeah. Problem 9, undamped forced oscillation with resonance. Okay. Yeah. Let's look at this example. Yeah. So let me explain. Yeah. Yeah. So in this figure, oh, yeah, this figure, yeah, actually, yeah. So you will see in part E today. So actually, I will work on this again. Yeah. So let's look at the question. Yeah, because here, undamped, right? Yeah, undamped, but this is the damping part, right? This dash part. This is the damping part, because that C we call the damping constant. Yeah. C is that damp constant. Yeah. Undamped, that means this constant should be 0. Okay. Yeah. No damping. Yeah. Undamped. Forced, then we need to have an external force, right? Yeah. We need to have an external force. R function. R function is the external force. Yeah. All right. That's the system. All right. Now, yeah. So the driving force, this is the driving force, external. Yeah. So here you can see there is a frequency. The driving force has its own frequency. Yeah. All right. Yeah. Can you tell me what is the frequency of the driving force? Yeah. Remember last time we defined the frequency. The frequency is reciprocal of the period. Yeah. What is the period of the driving force? Yeah. Sine, cosine, 2 pi, right? So 1 over 2 pi. The frequency here, 1 over 2 pi. Okay? Yeah. All right. What's that? Some extra. Yeah. 0 initial displacement and velocity. Yeah. For what frequency of the driving force would you get a resonance? Yeah. So this resonance phenomenon, very damaging phenomenon. So we need to pay attention. Yeah. So when we design a system, so we need to consider the potential damage caused by that resonance problem. Yeah. Solution. Yeah. Yeah. But here you can see, here actually the frequency is fixed, right? Because the driving force given, so the frequency here, frequency fixed. Yeah, fixed. All right. Yeah, but we can look at. Let us solve this equation. Yeah, m given, k given. So let's plug in. Yeah, initial condition also given. So the ODE is like that. Yeah. The question, next question, how do we solve this equation? Yeah. So this, here we do not use Laplace transform. Okay. Yeah. So if you use Laplace transform, so definitely you can find a solution easily. Here, let us practice our, non-Laplace transform skills. Okay? Yeah. So if you do not use Laplace transform, what do you plan to do? So any idea in your plan?
Since they're constant coefficients, could you do the method of undetermined coefficients?
Yeah. Right. Yeah. Yes. Undetermined. Right. Yeah. You can do that. But when you do that, do you have an idea what specific form your particular solution should take, right? Because we want to find a particular solution, right? The general solution is easy.
It's tough with cosine and sine.
Yeah. Not tough. Your particular solution also has the sine cosine structure, similar structure. Yeah, similar structure. Capital A cosine plus capital B sine, right? You include both sine cosine. But capital A, capital B undetermined. You need to determine capital A, capital B. Yeah. All right. So let's do it in that way. Yeah. We take, so here little a, yeah, it's fine. Little a, little b. All right. So, yeah. Then you plug in, yeah. So here, because that's the end of the presentation. Yeah. So actually, in part E, I will redo this one, but I will add omega t. Okay, I will change the function to omega t plus minus or plus minus sine omega t. That omega is unknown. The omega can change. Here, omega is 1, so fixed. Yeah, you cannot change. But when omega change, then omega appears at some special point, the resonance occurs. Okay? Because we want to study the resonance problem. Okay? When omega, we want to find that special point. Yeah. That, shows us resonance. Yeah. Yeah. So that's in part E, we will see it. Okay. Yeah. All right. Yeah. So here, yeah. So because next I will start part E. Yeah. I still have a few minutes. So let me see. So what is in part E? Yeah. What is in part E? Part E. So we want to see the title, Solution by Variation Parameters. Yeah. All right. Yeah. Because our part E, actually, when we start with that same problem, right? That old problem. Okay. Yeah. So I have 5 minutes, so probably, so I can, because we continue our old problem. Yeah. Probably we can finish that problem in 5 minutes. Because we are familiar with the equation already. All right. E.1, understand the resonance. So we want to see that resonance, where it occurs. All right. Yeah. So here now I change the figure a little bit. Yeah. Because this time the damping part, the damping coefficient, Oh. Yeah. Yeah. The damping coefficient equals 0. Undamped. Undamped, that means the damping coefficient equals 0. Then the damping term is gone. No damping term. Yeah. So let me explain. Here, you can see the y prime term, cy prime term is gone because this is the damping term. Okay? C equals 0. So cy prime, that middle term is gone. So that's the undamped system. Right? Then the driving force, here you can see we add extra omega. Yeah. So only when here we want to try different values of this omega, and we want to see at which value of omega we can observe that resonance problem. Yeah. All right. Yeah. The initial condition. Yeah. So the same way. Yeah. But this time y prime p. Yeah. And y double prime p. Yeah. And plug in to the original equation. Yeah. Yeah. So then combine the terms. Then we compare both sides. Yeah. Here, left-hand side, some constant part, then cosine function, constant part, coefficient part. Yeah. Then, what's wrong? Yeah. The coefficient is 1. The coefficient is -4, right? So, do you feel okay? We make this 1 equals the first block coefficient, -4 equals the second block coefficient. Do you feel all right? We can make that. Yeah. Yeah. All right. So why? Can you think about why? Yeah. We can set it that way. Yeah. Why we can set it that way? Okay. Yeah. Here, I raise that question. All right. Because later we need to answer a similar question. So at that time we can bring this question back. Yeah. In our second half. Yeah. All right. So let's continue. Here, because we set two equations, we can find that undetermined little coefficient. A is undetermined, B is undetermined. Undetermined coefficient equals expression related to omega squared. And omega, right? Undetermined B equals an expression with certain omega. Okay? Now, can you tell me, when you look at the form of A and B, can you see some potential problem there? A and B. Anything you can see, something could be wrong. Domain, yeah, related domain, yeah. How about when omega equals 3? What would happen? Undefined. How about close to 3? Close to 3, it's defined, right? It's defined. Denominator becomes very close to 0. The fraction value, yes. The fraction value extremely large, right? Yeah, think about it. Then your AB could be very large. Your solution, AB part very large. That's the resonance. Yeah. So here it explains why resonance occurs. Yeah.
Just like goes out of control.
Out of control. Yeah. And break your system. Okay. Yeah. So that's the, so after you solve this equation, finally you understand. So why it occurs like that. Yeah. All right. So now the break time. Yeah. So let's take a 10-minute break at 7:10. So you come back. So we continue the second half. Yeah. Yeah. I need to check my video. So if it's recorded,